Bismillahirrahmanirrahim. Assalamu alaikum students. Welcome to our 8th lecture of Business Math 1. Today we will start our 4th chapter, which is about mathematical functions. Our first 3 chapters were about some preliminaries. Second chapter was linear equations, and third chapter was systems of linear equations. Today we will see what do we mean by mathematical functions. So basically, what are the objectives of the chapter? To enable the reader to understand the nature and notation of the mathematical functions, to provide illustrations of the applications of mathematical functions, to provide a brief overview of important types of functions and their characteristics, and discuss the graphical representation of functions. Okay. What we will cover today? Mainly functions, the definition and some examples, domain and range of a function, and what do we mean by the multivariate functions. To identify the real mathematical representation of the real world phenomenon is done by mathematical modeling. So if a model is a good approximation, it can be very useful in studying the reality and making decisions related to it. In mathematical models, that is when we are identifying our real world problems into the mathematical terms, the significant relationships are typically represented by the mathematical functions or simply functions. So basically, whenever we want to transform our real world problem into the mathematical form, first thing we need is the functions. What do we mean by the function? Generally speaking, it can be viewed as a device, as an input-output device. That is, we give some input and we apply the function and we get some output according to the function defined. Then the set of inputs, there can be one input or many different inputs, is provided to the mathematical rule, which transforms the input into a specific output. By specific, we mean that it will give us the output according to our mathematical rule. For example, if we consider our equation y is equals to x, it is a linear equation. Then in this equation, our input is the selected values of x. We can take one value of x as an input or many different values of x as an input. Then the mathematical rule which assigns this input a new output is simply x, and output is the corresponding values of y obtained from the equation or the mathematical rule. What do we mean by this? That is, our equation is y is equals to x, and we have our input here, that is the selected values of x, and what are we doing? We put the values here in the function y is equals to x, the rule, and it gives us our output, which is y. Or for example, if we consider our equation y is equals to x square plus 1, then in this case we have our x as the input, the values of x or the selected values of x will be the input. Then we apply our rule, mathematical rule, which is x square plus 1, that is whatever the value of x we are getting, we will square it first and add 1 to it. This is our rule here, and the result we obtain after solving this value for x, we obtain our output, which is y. So this is basically a function. This mathematical rule in the second example, x square plus 1, is the function. That is, according to this rule, whatever the input x is, we are getting the output y. According to first example, here the mathematical function is simply x. Whatever the input is, we are getting the same output. So function is basically an input-output device. We are provided with a set of inputs. We apply the mathematical rule to the set of inputs, and then we obtain the corresponding output. Mathematically, what do we mean by a function? A function is a mathematical rule that assigns to each input value one and only one output value. That is, for one input value there will be only one output value. What do we mean by one and only one here? That if we have one input, only one output will be given for that particular input. Now, in the previous slide we have seen that we have talked about input or set of inputs. So the domain of a function is the set consisting of all possible input values. So all possible values of x in our previous two examples, that is in our first example y is equals to x, all possible values of x will be our domain. In our second example, all possible values of x will be our domain for the mathematical rule x square plus 1. Okay, so the domain of a function is the set consisting of all possible input values, and the range of a function is the set of all possible output values. That is, whatever the value of y is after applying the mathematical rule is our range. What do we mean by this set of all possible input values and set of all possible output values? First we have, let's say this is our domain, and this is our mathematical rule, okay, and this is our range. Here we call it x, here we call y. Let's say here we have 2 points and here we also have 2 points. Then we apply the mathematical rule to 1 point and it maps to 1 point. For the second point we apply the mathematical rule, it maps to the second point. So the set of all possible x will be the domain in this case on the left hand side, and the set of all possible y we are obtaining after applying the rule is the range in this case. Now this is an example of a function, because what we have emphasized in the definition of a function, that for each input there exists only one output. To each input value one and only one output value is assigned. That is, for each input on the left side in the domain only one value is assigned. Okay, so this is a function. Let us consider one more example. Here we have x, here is our mathematical rule, and here we have y. The same thing, the all possible values of y will be the domain, and the all possible values of x will be the domain, and the all possible values of y will be the range. Now we have, let's say, 3 points in our domain and 2 points in our range. What are we doing after applying the rule? This thing. The second one also goes to the first one, and the third one goes to the second one. So is this a function? Well, if we look at the diagram, we say that yes, this is a function, because to each input only one output is assigned, one and only one. Let's say if we call them 1, 2, 3, and here we call as A and B, then to each input 1, only one output A is assigned. To input 2, only one output A is assigned. To input 3, only one output B is assigned. So this is basically a function. Okay, one more case. This is our domain. All the possible values of x, our rule, and this is our range, all the possible values of y. We consider 2 points here, and we consider let's say 3 points here. Then let's say this is point 1, 2, and here we have A, B, C. Then we ask ourselves that is this rule defined as a function or not? If we look at our input 1, the rule assigns to input 1 two values A and B. This is not allowed in the definition of a function. To input 2, it assigns only one value C. It is okay, but for input 1 we can have only one output, either A or B. So this type of definition or this type of rule defined is basically not a function. That is, here to the input 1 we have assigned two different outputs, which is not allowed. Okay, now we look at some daily life examples. That what do we mean by the rule? By the rule we mean that, for example, the size of crowd at the beach may depend upon the temperature and the day of the week. That is, one thing, the output, which is the size of the crowd, is depending upon the temperature and the day of the week, which is basically the input here. In our second example, the price of taxi depends upon the distance and the day of the week. That is, the price is depending upon the output, which is the price, is depending upon two inputs, which is the day of the week and the distance covered. Similarly, the fee structure depends upon the program and the type of education, that whether the education is on campus or off campus. That is, the output, which is the fee structure here, is depending upon some type of rule. The rule is depending upon some values of input, which are the type of education and the program you are admitting in. Similarly, in the previous example, the price is the output function depending upon the two inputs, that is the distance and the day of the week. Now we have seen what do we mean by a function, a proper mathematical definition, and generally what do we mean by a function. We have seen some daily life examples, that what do we mean by the output, and the output we obtained is depending upon some previous thing according to some rule, so that rule will be the function and that previous thing will be the input. So if you want to write these functions mathematically, definitely we need some notation to write them. So from all these examples we have seen that the language of mathematics, in particular mathematical functions, describes how variables are functionally related. In our daily life examples, the price of the taxi is one variable. It is related to the day of the week and the distance traveled. The assigning of output values to corresponding input values is often called as mapping, and the notation we use f colon x arrow y. This notation represents the mapping of the set of input values of x into the set of output values y using the mapping rule f. Now the equation y is equals to f of x denotes the functional relationship between two variables x and y. That is, if we want to say it, y equals f of x, or y is a function of x. Here f is the rule which is assigning the input values x and the output values y. That is, x is the input variable. The rule which is assigning or describing the relation between input and output is f, and the value of y depends upon and uniquely determined by the values of x according to the rule f. So mathematical function is a rule which assigns a relationship between input and output. And how we denote it or write it mathematically? By y is equals to f of x, or f is equals to x mapping to y. Okay, for the input variable we have some particular name, that the input variable is called the independent variable and the output variable is called the dependent variable, because according to the rule we can take any selected values of input, we apply the rule to our domain, and we obtain the corresponding values of output which are depending on input according to the rule. So the naming is very clear, that independent variable is the input variable and dependent variable is the output variable. It is not necessary that x and y will always be the dependent and independent variables, and f will be always the rule relating x and y. Once we understand that what is the notation of a function, then we can easily identify the input variable and the output variable and the rule relating them. For example, u is equals to g of v is a mathematical notation of a function where v is the input variable, u is the output variable, and g is the rule relating u and v. Let us consider one more daily life example, the weekly salary function. Imagine that you have taken a job as a salesperson. Your employer has stated that your salary will depend upon the number of units you sell per each week. So if y is the weekly salary, that is, we can translate this mathematical problem into our mathematical terms. If y denotes the weekly salary and x denotes the number of units, x denotes the units sold per week, then here y, the weekly salary, is depending on the number of units sold per week. So x will be the independent variable and y will be the dependent variable, and the function will be y is equals to f of x. That is, f is the rule relating between the weekly salary and the number of units sold per week. That is, the dependency of the weekly salary on the units sold per week is represented as y is equals to f of x, where f is the name of the salary function. Okay, suppose your employer has given you the following equation for determining your weekly salary, that is, y is equals to f of x, which is equals to 3x plus 25. Then if we are given any value of x, which is the number of units sold per week, then it will result in the value of y with respect to the function f, or with respect to the rule 3x plus 25. For example, if x is equals to 100, then y will be equals to 3 into 100 plus 25, which is 325. And in this case, when we have some specific value of x or some specific value of the input, we write it as y is equals to f of 100. That is, f of 100 is basically giving us 325. So what is happening here? Here we have our input. Input is the number of units, x is the input, number of units sold per week, and here we have a mathematical rule f, which is 3x plus 25, and we are obtaining our output, which is y, which is basically the weekly salary. Okay, let us consider one more example, which is mathematical one. If we are given the functional relationship z is equals to h of t, here we can easily identify that t is the independent variable or t is the input, z is the dependent variable or z is the output, and h is the rule connecting z and t, and we have defined it according to the rule t square plus t minus 10. Then first thing we want to find h of 0, that is we will simply put the value of t is equals to 0 in our given rule or given function. So we will obtain 0 square plus 0 minus 10, which is equals to minus 10. Second thing, we want to find the value when t is equals to minus 5. Again we will do the same thing. We will put the value of t is equals to minus 5 in our equation. We obtain minus 5 square minus 5 minus 10, which is equals to 10. Suppose we want to find the value of h at some point u plus v, then here instead of t we will put the value of u plus v, and we will get u plus v whole square plus u plus v minus 10. Simplifying, that is opening the square first, we obtain u square plus v square plus 2 uv plus u plus v minus 10. So if we are given a function and some specific value of input, for example here in part A the specific value was 0, in part B the specific value was minus 5, then we can easily find the corresponding value of output according to the given rule. And in part C we have seen that the specific value will cannot only be a number, but we can have any arbitrary value, for example u plus v in part C. Okay, one more example. We are given the relation t is equals to u of v, which is equals to 2v square minus 5v. Here v is the input, t is the set of outputs, and u is the rule connecting t and v according to the rule 2v square minus 5v. And we are interested in finding the value of u when v is equals to minus 5. What we will do, we will put the value of v is equals to minus 5 in our given rule. We obtain plus 25, which is 75. Okay, we are further interested in finding the value of the output when the given input is x minus y. Then we have to put the value of v is equals to x minus y, and we obtain 2 into x minus y whole square minus 5 into x minus y. It is just a simple equation, linear equation in two variables. We will open the square first and the bracket. So what do we get? 2x square plus 2y square minus 4xy minus 5x plus 5y. Now we have seen few examples where we were given a function and we have calculated the function or the value of outputs at some particular value of inputs. Now we have seen different ways to define a function. First way is when we define the function in words. For example, if we have the output function is square of the input function, The output function is square of the input function. That is, whatever the input x is, the output function is simply its square. Or the output function is square of the input function plus 1. That is, whatever the input is, the output function is square of it and adding 1 in it. But in words we have seen that this method is not so easy and practical. When functions involve more variables or more terms, for example, the input function is x and the output function is x cube minus 3x square plus 4x plus 80. To describe this function in words is not so pleasant. So we have definitely other ways to define a function. The second option is by using a formula. For example, x square, in our previous example, x square plus 1. These formulas represent that for the set of inputs, the output is x square or x square plus 1, or simply t cube minus 3t square plus 4t plus 80. Now in this case we know the input variable and the corresponding values will be the output values. Third way to define a function is by using a mapping diagram. A mapping diagram, we have already seen, is nothing but this is our possible values of inputs, this is our possible values of outputs, and we have some rule in between assigning to each input only one output. For example, this is our rule f, this is x and this is y, and we say the set of x is the set of children and the set of y is the set of mother. Let's say we have 3 children in our set x and 2 mothers in our set y. We call them A, B, C and 1, 2. Then if a child A is assigned to mother 1, a child B is also assigned to mother 1 and child C is assigned to mother 2, then is this a function? If we are given a mapping diagram, we can easily see that what are the input values, what are the output values, and what is the rule. Though we cannot write it mathematically easily, but we can see with the help of my mapping diagram that is the given rule is basically a function or not. In this case, what we have, each input has only one output. Definitely, if we look at our set of outputs, that is the set of mothers first, then a mother can have 2 child, but a child cannot have 2 mothers. So definitely, if A is corresponding to 1, B is corresponding to 1 and C is corresponding to 2, then this rule or this mapping diagram represents the function. Let's consider this mapping diagram again. We have this as our x, that is the set of children, and this is our set y, that is the set of mother, and f is the rule. Let's say we have 3 children. How we have named them? A, B, C, and 2 mothers, 1 and 2. Okay, if a child A is assigned to mother 1, fine. A child A is also assigned to mother 2. This is not possible. According to the definition of rule, child B is assigned to mother 1, fine. Child C is assigned to mother 2, fine. But child A, that is the input A, has 2 values, 1 and 2, which is not possible according to the definition of function. So this mapping diagram does not represent a function, and we say that it is not a function. Okay, one more time just to make it clear, what do we mean by a function? We have set of inputs x again as children, set of outputs y as mother. Our rule is if we have 3 children and 2 mothers. We call them A, B, C and 1, 2. Okay, child A is assigned to mother 1. Fine. Child C is assigned to mother 2. Fine. So, does this mapping diagram represents a function? Well, if we say that every input has exactly one output, fine, but what will happen to the first part of the definition, which says that to each input, here the input B, that is child B, is not assigned to any value from the set of mothers. This means that this input, according to the rule F, should have some output. So this mapping diagram does not represent a function. For example, one more time, x and this is y. This is our rule F, and what is happening here? This is assigned to this value, this is assigned to this value, and this is also assigned to the second value. So is this a function or not? Then this is a definition of function. This satisfies the definition of function because to each input, every input should be covered. If one output is not covered or not assigned any previous input, then there's nothing to worry about. Each input should be covered, should be assigned some value y. Here all the 3 inputs have assigned some value y, and every input has unique value. That is, no input in set X or in this domain has assigned 2 values in the set Y. So this is a function. Okay, our fourth way to define a function is by using an equation. By using an equation, we mean that, for example, y is equals to x square. When we write y is equals to, means we are using some equation, and this equation represents a function or not, but it is one way of representing a function by using an equation. Or for example, y is equals to x square plus 1, or s is equals to t cube minus 3t square plus 4t plus 8. From these equations, we can easily identify the dependent variable and the independent variable. That is, the quantities on the right hand side are the set of inputs or the independent variables, and the quantities on the left hand side are the set of outputs or the dependent variables. Okay. Now we want to see what do we mean by the domain and range of a function. We will focus only on real valued functions, so that the domain consists of real values of the independent variable, for which the dependent variable is defined and real. In order to find the domain of a function, let's have a look at some examples. If we have an equation y is equals to f of x, which is equals to x square minus 2x plus 1, then any possible value of input will give us the real valued of output. If capital D denotes the domain of the function, then how we write it mathematically? All the values of x such that x is real. That is, in this case, all real valued of x are allowed to be as a set of input or to be as the set of domain. Or in other words, domain is the set of reals. Okay. Why the set of all reals is the domain? Because the function is defined for all possible values of x, which are the real numbers. There is no value of x for which the function is not defined. So in this case, the domain is the set of all real numbers, and every real number will give us, after the rule f, as the real value as the output. So the domain will be the set of all reals. This was the example 1 which we have. Okay, let's consider one more example. Y is equals to x minus 3. Then this is a linear equation in x and y, and here if we take any value of x from the set of reals, the output or the value of y will again be a real number. So in this case, we will have our domain as again the set of reals, that is x, vertical line, which mathematically you say that such that x is real, or our domain is the whole real line. Because as in the case of previous example, there is no value of x which gives us some value of y which is not a real number. Okay, one more example. We have u is equals to f of v. V is the set of inputs, u is the set of outputs, defined by 1 over v square minus 4. So this is our rule. Now we want to find our domain, that is the possible values of v which gives us the real value of u after the rule f. Now in this case, clearly the points where the function is not defined will not include in the domain of a function. That is, the points where we cannot define a function, where we have some undefined form, those points will not be a part of the domain of a function. So in this example, here we have u is equals to 1 over v square minus 4. The function is not defined for some values when the denominator is 0. That is, in particular, when v square minus 4 is 0, because when the denominator will be equals to 0, the function will not be defined anymore, and the value of u or output will be undefined. So if we solve this equation, we obtain v square is equals to 4. We have already done in chapter 1 that how we can solve our linear equations and quadratic equations, and we obtain the value of v is equals to plus minus 2. That is, the denominator will be equals to 0 when the input value v is equals to either 2 or is equals to minus 2. So these two values will not be included in the domain of the function. In this case, the domain will be the set of v such that all those real values of v real and v is not equals to plus 2 and minus 2. If v is equals to plus 2, our denominator will be equals to 0, the function will be undefined. If v is equals to minus 2, the same happens, that we obtain an undefined function. So in this case, it was easy to find the domain, and it was clear that the domain will be the set of all reals except plus 2 and minus 2. Okay, our third example is y is equals to f of x, which is under root x minus 5. Now here we have some rule which consists of under root or square root, and we are only talking about real valued functions. That is, the set of input or domain will be the set of reals or a subset of real. A subset of real we have seen in our second example, and the value of y, or the input, will also be a set of reals or a subset of real. So in this case, the square root is not allowed to be of a negative number. If we are only restricted to real valued functions, then any value of x which gives us the negative square root is not allowed. In other words, what we are trying to say, that all those values of x are allowed, or all those values of x will be in the domain whenever this square root is positive. That is, whenever the number x minus 5 is equal to 0 or greater than 0. Solving this inequality, we obtain x is greater than equals to minus 5. We can easily solve it by adding 5 on both sides. So whenever x is greater than equals to 5. So whenever x is equals to 5, the square root is 0 and the output is 0. Whenever x is greater than 5, again the output is positive. So in this case, our domain will be D x such that x is real and x is greater than equals to 5. Or once we know that we are only talking about real valued functions, that is the real valued input and the real valued output, then we can easily write our domain as, and we know what do we mean by x, that is the set of inputs, x such that x is greater than equals to 5. When it is clear to us that we are only talking about real valued functions, then we can skip this condition that x is real from our domain, and we can simply write x such that x is greater than equals to 5. Let's have a look at one more example, which is very interesting one, and it is of a quadratic equation. Y is equals to f of x, which is equals to x square plus x minus 12 under root. Okay, now here we have under root, which means that only those values of x as input are allowed which gives us the output under root positive. So our domain will be x square plus x minus 12 greater than equals to 0. That is when we will simplify. If we recall from our first chapter, this is a quadratic equation in one variable, and we can easily find the roots of this equation, that is the values of x which satisfy this equation. And in our first chapter we have done so by two methods, by factorizing and by using the quadratic formula. Here we can easily make our factors as x square plus 4x minus 3x minus 12 greater than equals to 0. Simplifying we obtain this, and our two factors are x plus 4 and x minus 3 greater than equals to 0. Okay, now we have a product of two terms greater than equals to 0, which means that x plus 4 and x plus 3 greater than equals to 0, which means that either both are positive, that is we are multiplying two positive things and we are obtaining something positive, again greater than 0, or either both are negative, which results in a positive number. Okay, let's have a look when both are positive, that is x plus 4 is greater than 0 and x minus 3 is greater than 0. Solving this inequality, we obtain x is greater than minus 4 and x is greater than 3. Okay, what does this mean on our real line? This is x 0 3 minus 4. X is greater than minus 4 means from here onwards continuing. X is greater than 3 means from here onwards continuing. Okay, here we have and in between. We should remember that we have and in between, that is when both are positive the product is positive, or when both are negative the product is negative. That is when x is greater than -4 and x is greater than 3 the product is positive. Second case, when both are negative, that is x minus 4 less than 0 and x minus 3 less than 0. Simplifying, x is less than 4 and we have here plus 4 and here minus 4, and x is less than 3. Back to our diagram. X is less than -4 means from here onwards. X is less than 3 from here onwards. Combining these two, what do we obtain basically? Okay, first condition says that since we have and in between, it should be greater than -4 and greater than 3 at the same time. So what do we obtain? That x is greater than 3, and from our second condition that it is less than -4 and less than 3 both at the same time, taking the intersection we obtain x is less than -4. So our domain is the set of x such that x is less than equals to -4 and x is greater than equals to 3, or in particular we obtain our in the interval form -infinity to -4 closed from this side, because here we have less than equals to union close bracket 3 to infinity. So our domain is basically the union of two half open intervals -infinity to -4 and 3 to infinity, and not the whole real line. In fact, it is a subset of real line. Let's talk about some word problems again. There we see the notation of restricted domain and range. So up to now we have solved mathematically to find the domain of some types of functions, but for some real world problems there may be more restriction on the domain. For example, in the weekly salary equation, which was y is equals to 3x plus 25, where x is the number of units sold per week and y is the weekly salary. Okay, now from this problem we see that the number of units sold per week cannot be negative. That is, the value of x cannot be negative. So the domain in this case will be the set of all positive real numbers so far. That is, D will be x such that x is greater than equals to 0. Equals to 0 is possible because it is possible, it is more likely that no unit is sold in 1 week. Then definitely the number of units sold each week will be minimum 0 but cannot be negative. Also they cannot be in fractions, either a unit sold or not. It is not possible that only 1/3 of a unit is sold. So we have two restrictions according to our daily life example or real world problem, that the domain cannot have negative values and the domain cannot have non-integer values or fraction values. So in this case our domain will be x such that x is a positive integer. That is, x cannot be negative, x cannot be in fractions, so the domain will be only the set of all positive integers. Okay. Now, if, for example, the employer also put an extra condition on the maximum number of units sold per week, that the minimum is 0, we know, but the maximum number, that you cannot sell more than 10 units in 1 week, then in this case the domain will be defined as D bracket x such that 0 is less than equals to x is less than equals to u, where u is the upper limit or the maximum number of units sold per week. In this case, the range will also be in integer values, and it will not be less than 0, because if there is no unit sold in 1 week, then the range or the output will be will be 25. If r denotes the range, then how we will write our range as y such that 25, because our equation was y is equals to 3x plus 25. So if no unit is sold in 1 week, that is when x is equals to 0, the minimum value or the minimum output will be 25. 25 is less than equals to y is less than equals to 3u plus 25. Okay, so far we have discussed only the functions in one independent variable. There are many mathematical functions in which the value of the dependent variable depends upon more than one independent variable. Now, functions which contain more than one independent variable, they are called as multivariate functions. That is, they are depending on more than one input at the same time. For example, the price of taxi is depending on the distance and on the day of the week. Is depending on more than one input at the same time. In most real-world problems, many variables interact with one another. For example, if a function is depending on two inputs, or if a function have two independent variables, then it is called a bivariate function. And these functions are denoted by z is equals to f of x, y, where f is the rule relating between z, x and y. X and y are the two independent variables or the two independent set of inputs, and z is the dependent variable or the set of output. For example, if we have z is equals to f of xy, which is equals to x square minus 2xy plus y square minus 5, then this is basically representing a function of two inputs x and y according to this rule, and the output z. If we are interested in finding the value of the output when the given input is 0 and 0, that is when both the independent variables have the value 0 and 0, then we obtain our output as 0 minus 0 plus 0 minus 5. So in this case the output will be minus 5. And what do we mean by the function, or by a bivariate function in the sense of mapping? That is, this is, let's say, the set of all ordered pairs x and y defined by the rule f of xy and giving the output z. Let us consider one more example. When we have z is equals to f of xy, which is given as x square minus 2y square plus 4xy over 3x minus y. So in this case, the numerator is defined for all ordered pairs x and y, but the denominator is not defined for all ordered pairs x and y. In this case, what do we mean that here we have our coordinate x's and this is our domain. We are assigning this set of domains our rule f, and we are getting our input z. That is, from 2 dimension we are, after applying our rule f, going to 1 dimension. Okay, let's come back to the point that the denominator is not defined for all values of x, y. Clearly, if we want to find the domain of this bivariate function, we have to find the values for which the denominator is not defined. That is, we want to find the values where the denominator is actually 0, or in other words, this gives us 3x is equals to y. So this combination of ordered pairs, whatever the value of x is, for example, if x is 1, the value of y will be equals to 3, and there are infinitely many ordered pairs satisfying this relation. So all the ordered pairs satisfying this relation do not belong to the domain of the bivariate function z is equals to f of xy. So the domain will be, if you want to write, that is the ordered pairs x and y such that 3x minus y is different from 0. Or we can also write the domain of all ordered pairs x and y such that 3x is different from y. That is basically, if we want to plot this linear equation in 2 variables x and y, here it is of the slope-intercept form, y is equals to mx plus c, with c is equals to 0, then we know that these type of equations definitely pass through the origin. That is, when x is 0, y is 0, so but the slope is positive, which is 3, so the line will be drawn passing through the origin from left to right. So this is the equation of a line 3x is equals to y, and this line is not included in the domain. Okay, first we have seen an example of bivariate functions. Now we go to the general concept. That is, if we have a function which has more than 2 independent variables, then the multivariate function is written as y is equals to this output is equals to f, which is the rule of inputs x1, x2, x3 and so on up to x4. That is, it is a function of up to xn. That is, it is a function of n inputs or n independent variables. For example, if we have y is equals to f of x1, x2, x3 and x4, that is our function of 4 inputs as x1 square minus 2x1 x2 plus x cube square x4 minus 25, and we want to find the value of output when the given input is -2, 0, 1 and 4, then we will simply put the values of x1, x2, x3 and x4 in our equation, and we will simplify it. That is minus 2 square minus 2 into 2 0 plus 1 square into 4 minus 25, and we get as minus 17. With this, we have some questions from our follow-up exercise 4.1, question 1 to 43 and question 52 to 60. Okay, let us summarize what we have done today. We have studied the functions, their definition, then the ways to define a function. Basically, we have studied 4 ways to define a function. We have also seen that what do we mean by the domain and the range of a function, some examples to find the domain of a function, and what do we mean by the multivariate functions, that is the functions having more than one independent variable, how we can find the domain of such functions in the case of bivariate functions, and how we can find the value of output at some specific value of n. In our next lecture, we will continue with chapter 4, and we will study about the types of functions and the graphical representation of functions. With this, we end our today's lecture. I hope the definition of function and the concept of function was clear to you with the help of examples, and you can easily find the domain of the function. With this, Allah Hafiz students, see you in the next lecture.